So I want to go back. I finished very quickly yesterday evening. I just wanted to go back on some of the slides that I skipped through at the very end and revisit those. Okay. So I was here and I was talking about the importance of continuous mechanism development and saying that we've made a lot of progress, right? But we still, more work is needed. Okay. So, and I spoke about the common core mechanism here for acetylene. Okay. Okay, it doesn't seem to be working. Okay. The, yeah, the pointer doesn't seem to be working. Okay, no, it's not displaying on the screen. I think it's a problem with the screen. Okay, so it's just the screen. Okay, and what I showed here was that in all the mechanisms except that from Peter Glarborg's group, this acetylene plus HO2 reaction was missing. And adding that reaction and then the oxidation of the radical produced in the reaction led to good agreement with the experimental data, okay? Which I suppose the point of this is that just making the mechanism and not considering this product, okay, or not doing a potential energy surface analysis would make you miss a very important reaction in the mechanism. And there's a big, big difference in the prediction of the solid line in comparison to the other lines on this graph, right? It's much more accurate, right? And so to develop accurate models, a systematic approach to determine the potential energy surface is needed. Really, that's the conclusion I want you to take from this, right? And so we typically now, more and more, we're going in the direction of using automated codes to do this. Okay, so this is just another example, and I had this in an earlier slide. I just moved it here now. I was looking at this morning. So just to tell a very similar story for vinyl plus O2, and vinyl is very, very important. I have a slide probably tomorrow that I'm going to show you. So ethylene is much faster than other species to ignite. So remember yesterday I spoke about methane being the slowest, ethane being the fastest, and then the others were intermediate. And that's because the radicals that you get from the daughter radicals are hydrogen atom and methyl radical. And you only get methyl radicals from methane. You mostly get hydrogen atoms from ethyl, but you also get ethylene. And ethylene in itself is a very reactive fuel. Why? Because of the reaction of vinyl radicals. So you abstract a hydrogen atom from ethylene, you get vinyl radical. And then vinyl radical goes on. And prior to 1984, I'd stand here at the maybe can I had pointer options, laser pointer. So prior to 1984, it was assumed that this reaction just occurred. Vinyl plus O2 gives acetylene plus HO2, okay? But then Irene Slagle, I don't know when that was, about 1990, I think, 1984, sorry, did some experiments and working with David Gutman. Irene Slagle, working with David Gutman, right, they found that at temperatures below 900 Kelvin, that this reaction actually produced formaldehyde and formal radical, right? And formaldehyde and formal radical will give you a high degree of reactivity because formaldehyde will oxidize to formal radical, and formal radical can undergo unireactor decomposition to give H atoms. And then H is going to react with O2 to give O plus OH. So that's going to significantly increase reactivity at temperatures below 900 Kelvin. So it was then Phil Westmoreland and Joe Bozzelli and Carpenter and Mebel, all of these groups working in the early 90s and mid-90s, calculated, because vinyl plus O2 is actually like really important, right? And chemical kinetic mechanisms are very sensitive to its oxidation kinetics. They all confirmed the low temperature pathway and indicated another important pathway at high temperature. So actually at high temperature, vinyl plus O2 gives vinoxy plus O. That's also a very important reaction, right? So it's dangerous to optimize mechanisms when critical features of potential energy surfaces are not fully understood, right? And so it's best to use the quantum chemistry calculations to inform us about what the potential energy surface actually is and what are the product species produced in reactions. Okay, and Franklin Goldsmith, working with Stephen Klippenstein and others at Argonne National Laboratory, did state-of-the-art quantum chemistry calculations on the vinyl plus O2 system. And that they calculated rate constants as a function of temperature and pressure, confirming the low temperature formaldehyde plus HCO route and also the vinoxy plus O route, and with a crossover temperatures about 1,000 Kelvin at 1 atmosphere. But note that actually C2H3 plus O2 stabilizes to C2H3O2 radical at pressures above 10 atmospheres. So having accurate kinetics for the whole system, you can now simulate pressure dependent, higher pressure, and like the pressure dependence of the system also. So it's really important to have that accurate high fidelity chemical kinetics in your model. Okay, and so it wasn't really until this rate constant was published 10 years ago that we were able to button down the mechanism in predicting larger hydrocarbons like ethane, or even larger ones, because larger hydrocarbons produce a lot of ethylene and propene. Okay, and so having accurate ethylene chemistry is very important in your mechanism. Okay, so a lot of mechanisms now are being developed, and I'm going to just highlight some. One was proposed by Judith Zador and Hajib Najim at Sandia National Laboratory. It's called KinBot. That was used by Judith Zador and Jim Miller to explore the C3H5O potential energy surface in this paper published 10 years ago at the Combustion Symposium. We have also then now, it's ESTOKTP, and this stands for electronic structure to rate constants as a function of temperature and pressure. Okay, and this is a code that was developed jointly by Stephen Klippenstein, largely by Stephen Klippenstein and Carlo Cavallotti, working also with Bill Green's group at MIT. And this is, again, a code that can be used to calculate rate constants based on the potential energy surfaces of reactions. Okay. And then you also have AutoTST. This is from Richard West's group, and there's a link here. I included the link. It's not in your original notes, but there's a link here and the reference to the automated transition state theory calculations for high throughput kinetics. Okay, so there's codes now that you can use to do these calculations for you. Really, that's the point. Okay. Okay, so developing then and optimizing detailed chemical reaction mechanisms. GRI approach employed by Michael Franklock, David Sheen, Hai Wang, and Thomas Turiani and all. We can look at that. I might highlight that in a second. Jim Seary used Monte Carlo method in 2001, but really what you need, or what comes from that, is that the more direct and indirect measurements you have of rate constants, and the more accurate they are, then the more successful the optimization, right? Which makes sense, right? So, okay, so rate constants can be measured directly. They can be calculated using high-level quantum chemistry calculations, and they can be optimized against an extensive range of experimental validation targets. And sometimes the targets are telling you what the rate constant needs to be. So for instance, I showed you yesterday how Ron Hansen measured, or backed out the rate constants for H, the rate constant for H plus O2 giving you O plus OH by measuring the water profile. And then the mechanism was extremely sensitive. Sorry, the rate constant for the H plus O2 giving you O plus OH, the choice of rate constant for that reaction, the prediction of the water profile was really sensitive to the rate constant that you use for that. And based on that, he was able to back out the rate constant. Okay, so we can do that sometimes with data that we measure. Okay, so I would encourage you to have a read of this work as well. It's an optimization of a hydrogen combustion mechanism using both direct and indirect measurements. And in here, it describes the work that was done by Michael Franklock, David Sheen, and Hai Wang. And essentially what they were doing, and I hope I get this right, and I don't mean any offense, what they were doing was taking what I just said there, a series of direct and indirect measurements, assigning uncertainty bands to the measurements and the experiments, the experimental measurements, and the calculations, and then backing out or allowing the mechanism, to be optimized within the band of uncertainty for the rate constant, and taking all the rate constants in the mechanism and doing that. Okay, there's a problem with that, and sometimes, and the biggest issue with that is if the rate constant falls slap bang in the middle of the band, that's very nice. But if it's at one extreme or the other of the band, that's worrying. Okay, and another thing in that Michael Franklock and David Sheen and Hai Wang, Michael said he argued with me about this after a meeting, but I can't see evidence of it. Certainly initially, what they did was they only optimized the frequency factor. They didn't optimize T to the N, and they didn't optimize the activation energy. If you only optimize the frequency factor, then your reaction mechanism will only be valid within a narrow range of validity, right? Whereas if you optimize all three, A, N, and EA, then your mechanism will be valid over a wider range of conditions. And so that was most of the advance that was done in this work in 2015. Okay, now Hai Wang and David Sheen have moved on since, and now they are optimizing mechanisms now, adjusting all parameters in the rate constant expressions. All right, so it's not just that. Okay, and the question then is the computer better than human? And I would guess yes, of course it would be, because it can do it better. Okay, so here's the ranking of mechanisms. Okay, and just to say, look, the Curran mechanism, NUIG mechanism, the 2010 one, the 2013 was better, and this one was 2015. You can see that this is the ranking. And so by hand, we were able to do it pretty good, but you can do it better by computer. So the computer optimization is on top, okay? And it's faster, and the uncertainties are much lower, okay? So the average shock tube uncertainty is 5.94%. Ours was 6.69. For RCM, it's 6.7. Ours was 11.3. So you can see that the uncertainty is much lower in the computer optimized mechanism. Okay, so you can look at go to these databases. You have the Prime website by Michael Franklock and co-workers. You have CloudFlame website from Mani Sarathi. You have the Respect database from Thomas Turiani's group. I have links there to these different websites. It's a slightly modified form of Prime, basically the Respect database. It contains files of the direct and indirect data to be processed. Okay, so it's a good resource for taking data and for optimization of a mechanism if you want to target specific species. Have a look at it and you can see. ChemKed was being developed by Weber and Niemeyer, and I don't know how much more work has been done that in recent years. And you have ChemConnect from Ed Blurock, which is here. So you can check those out and just see how current or how developed all those different databases are. Okay. So just then to say that mechanisms for small molecules, they've been developed and published over many years. Back in the 90s, there was a methane natural gas mechanism from Philippe Daguet, methane ethane from Barbe et al. 1995. That was, again, from a French group. A Leeds mechanism published in 2001. This is going back a long time. The Miller-Bowman NO mechanism was first published in 1989. Small oxygenated species from Professor Dreyer here at Princeton from 1991 to 2007. And then GRI-MEC, which is still used a lot by industry in applications because of its small size and that it's easy to be used in CFD simulations. Okay, and it compiles quickly and everything. So it was used for natural gas, and it also included some prompt NO formation and reburn kinetics. Okay. So some more recent ones then, we have USC-MEC, developed by Hai Wang in 2007. This has graduated, and I should have FFCM2 now, not FFCM1. I should have updated the slide, apologies. But you can go to the Stanford website and you'll find the latest. What is it? I can't. Foundation Fuel Chemical Mechanism is what it stands for, FFCM, Foundation Fuel Chemical Mechanism. You've got the CREC, Politecnico di Milano core mechanism, and then it can be used with lots of other species, primary reference fuels, polyaromatic hydrocarbons, and so on. Okay. San Diego mechanism published by Foreman Williams. That's a quite popular small species mechanism. And Aramco-MEC from Galway, which we last updated in 2017. There were 3 different versions, 1.3, 2.0, and 3.0. And then the Glarberg mechanism, I have here Jimenez Lopez from 2016, but there's probably a more recent update. And again, if you go to, he's in Denmark. If you go to his website, you find links to latest mechanisms from him. Okay, these are all mechanisms that are freely available on the internet, or if you write to the author, they'll provide them for you or to you. Okay, there are other core small species mechanisms. You have ones from Wei Qi from the Shanghai Jiatong University, ones from University of Nancy from Frédéric Bajon-Leclerc. CNRS has their own, Philippe Daguet and his group. Chemkin Reaction Design. MIT, Bill Green has his own core chemistry. Lund University, Tokyo University, Technical University of Denmark, as I said, Peter Glarborg, and the CREC modeling group. Okay, so, okay, and I think I won't bother. Okay, so where do we get the rate constants then that we use in the mechanisms? Okay, previously there were reviews published by Cohn and Westbrook, Zhang and Hampson, Bausch et al. And also then we have the NIST Chemical Kinetic Database. I already have shared with you links on previous slides to that database. But in these reviews, rate constants were reviewed reaction by reaction. And then they recommended a rate constant based on the review. But the problem with that is, okay, the combined effects of the mechanism. So what I want to say is, if you took their review, their recommended rate constant, you put that into a mechanism, it wouldn't reproduce experimental targets very well. Okay, so the thing is that you actually then need to simulate the experimental targets and adjust the rate constants within their uncertainty to get good agreement of the model with the experimental targets. Okay, so you can't just take the rate constant from the review. If that would work, people would have done this many years ago. Okay, you still have to work on the mechanism. So in practice, comparisons are made and some optimization is performed. Okay, so I don't want to say much more. This is just hydrogen mechanisms. there, you have the slides on that. I'm not going to go into that. It's just, and I finished yesterday with this slide, and based on what I've just said, I think it might have more meaning for you than when I finished yesterday. But it's likely that all of these mechanisms for the small molecules would steadily converge, and they are. Like if you go to if you go to people's mechanisms and you look at the rate constants, often for many of these important reactions, and the ones I want to highlight, and I know I don't know whether you found it boring or not with all the detail that I went into yesterday. That is the detail as a kineticist that I have to go into to get a mechanism that works really well, and to get one that's really highly, what's the word? Well, I don't know, what's the word? Accurate in predicting all the experimental profiles. Okay, and I showed you how we do it by hand, right? I actually had a PhD student start. He just defended his thesis last week, and it was on optimizing mechanisms for alkanes, all alkanes, right? Everything, right? But when he started his PhD, I said, okay, you're going to be using a code to do this, and the computer will be doing the optimization for you, right? Because there's so much data and there's so many fuels that you can't do that by hand, right? But I don't want you to do that yet. So I had him work for 18 months doing it the way I just showed you, plotting the rate constants, looking at, doing all that rigor, so that he actually understood what the computer was doing. And he understood what was the nuts and bolts behind what's going on, all right? And so that's what I kind of feel the point of me giving these lectures is as well, okay? So that's a quotation from Charlie, and I actually strongly agree with him on this, okay? In the mechanisms now, a lot of the rate constants that we use are converging. And as we know more and more, and as I said yesterday, a rate constant, in my opinion, is God-given, right? We might know what it is, but it is a constant at a particular temperature and pressure. And if we can get those more and more accurately, then we'll have more and more accurate mechanisms that will be able to predict fuel combustion. Okay, so that's me caught up with day 3. Okay, and just move on to day 4 lectures. Okay, so that was yesterday was focused on developing mechanisms at at high temperature. Now I'm going to talk about developing mechanisms at low and intermediate temperatures, right? So the boundary between small and large fuel molecules is somewhat arbitrary. However, C5 fuels have much more low temperature reactivity than C4, and C6 fuels have much more low temperature kinetics than C5. So C6 and larger molecules have lots of low T reaction pathways, cool flames, and lower octane number values than smaller fuels. Okay, so the smaller fuels are less reactive. Okay, this is a nice slide. I just wanted, this figure is courtesy of Professor Tianpeng Liu, and it was actually, it's an extension of a figure that Professor Liu published with Professor Law in a Progress in Energy and Combustion science paper, right? But he updated this for me in 2019, okay? And their paper was published in about 2014. If you look it up, you'll be able to find combustion science, Liu and Law, right? It'll come up, okay? But what I've plotted here, and again, this isn't a new idea either, new concept. Charlie published this in a review paper with Jürgen Barnatz and some other people at the symposium, maybe 10 or more years ago now. Okay, and it's calculations per second per constant dollar as a function of year. And it's just, you can see that there's an exponential increase in the calculations that can be performed per dollar with time, right? So and this is Moore's law, right? And it's just saying, what he said was that there'll be an exponential increase in computing ability, ultimately, right? And that's reflected in the size of the mechanisms that were developed over the years, right? So there's a correlation between this plot here and this one here. So before 2000, we had mechanisms that could simulate C4, right? C1, C4, okay? And then from there on, we started to increase the size, the number of reactions, and the number of species in the mechanism. And now, you're up to 10,000 species and maybe 100,000 reactions or tens of thousands of reactions in mechanisms, okay? Because of the computing power that's available to us, okay? So when I was running the N-heptane mechanism back in 1995, 1996, right, that took maybe overnight to run the simulations, right, that could be done in probably a fraction of a second now, or seconds on the computers nowadays, all right? So, okay, so this is the paper that I'm talking about at the symposium, where he talks about, all the co-authors, they talk about the calculations and the link between Moore's law and the computing ability and mechanism development, okay? And they mirror one another is really just the point of this slide. Okay, so the mechanism size grows with the molecular size. So hydrogen, did I say 7 or 8 species and 25 reactions? If we have cetane, C16H34, about 1,200 species and 7,000 reactions, okay? So there's a big increase in the number of species and reactions with the size of the molecule, okay? So for nearly all hydrocarbon oxidation, no matter how large or small the fuel molecule, at high temperatures, the reactions of H2O2 have the greatest sensitivity to controlling the overall rate of reaction. And I showed that yesterday with H plus O2 giving you O plus OH is all important at high temperature, all right? And this is a nice slide from Professor Faravelli at the Politecnico di Milano. It shows at high temperature, because there's energy barriers to breaking these bonds, right? These are CC or CH bonds. There's a high energy barrier for that. And so at high temperature, what happens is that those barriers can be overcome because you're at high temperature. And so what happens is you get unimolecular decomposition of the fuel to smaller radicals, and then oxidation of those smaller radicals, giving you water and CO2, okay? And why is that? I'll just show you. Okay, so right here. So if we have, I don't know what molecule, 3, 4, 5, that's N-heptane. Okay, so we have NC7H16, let's just say, gives C4H9 plus C3H7. Is that all right? Okay, what is the rate of this reaction? Yeah, rate constant times the concentration of NC7H16. Okay. Okay. So what about NC7H16 plus O2 gives 1, 2, 3, 4 C7H15 plus H2O plus HO2. Okay, what about that one? What's the rate of this reaction? Okay, so if we have a typical fuel-air mixture, what's the concentration of O2? and the fuel, but O2 in particular, because, okay, I'll just take it to where I wanted to go for a second, right? And I'll come back, right? So this is, we'd say this is 1 and this is 2, okay? And actually, well, it happens that this is 2 and this is 1, but this is the first order rate constant, this is the second order rate constant, not a reaction. But if we have rate of 1 over rate of 2 then, so we have rate of 1 over rate of 2 is equal to K1 times the concentration of NC7H16, okay, divided by K2 times the concentration of NC7H16 times O2. Okay, so the relative rate of 1 over the rate of 2 is equal to K1 over K2 times the concentration of O2. Okay, if that's okay with everybody, right? So what if you're at high temperature, right? You can overcome the barrier to the formation of NC4H9 plus NC3H7. So K1 is quite fast, right? So the rate will be a fairly fast rate constant times then the concentration of the fuel, right? So the question then is, what's the concentration of the fuel if you're fuel in air? At, we'd say, 10 atmospheres. Okay, so I haven't done this in years. I can't remember exactly. Okay, so let me just try and do it roughly. So we have 1 part fuel, and we have, what is it? 11 O2, and then we have, is it 3.76 times 11? Let me just see. So 79 divided by 21 is 3.76. So that's correct, times 11 is equal to 41.38. So the total is 12 plus 12 is equal to 53.38. So the fraction is 1 divided by 53.38. 1 divided by, so it's 1.87% fuel. That makes sense, that rings a bell. 11 divided by, and 20.6% O2. Okay, so you have 77.52%. Okay, so if you have 1.87% fuel and you have 20.6% O2, you have, again now, let's just say we're at 1,000 Kelvin, or we have the concentration, we have PV is equal to nRT. So we have P over RT is equal to N all over V, which is the concentration. So what's if we're at 10 atmospheres, what's the partial pressure of oxygen? It's 0.206 times 10. So it's 2.06. 2.06 divided by 82 point, what is it? What's the number? No. It's in atmospheres, so it's 82.06 or something times 1,000. Okay, so R is in atmospheric units. Okay, so what's that? So it's 2 divided by 82.06 is equal to divided by 1,000. So it's 2.43 times 10 to the minus 5. Okay, so that's the concentration. Okay, so the concentration of O2 is 2.43 times 10 to the minus 5. Okay, if you're N-heptane in air at 1,000 Kelvin, right? So if we look here, the rate of 1 then is going to be the rate constant times NC7. But the rate of 2 is going to be the rate constant for reaction 2 times the concentration of NC7, H16, but that cancels. So it's going to, the relative rate is going to be K2 times the concentration of O2. But the concentration of O2 is, we'll say 2.5 times 10 to the minus 5 at 1,000 Kelvin, right? So it's decreasing that rate by 5 orders of magnitude relative to K1, or the rate of 1, I should say, right? Now, the rate of 1 at low temperature is much lower because the activation energy barrier. But once you get to about 1,000 Kelvin, they start to compete with one another. Why? Because you've got the high energy barrier for breaking the CC or the CH bond, but you, for the low temperature one, you have the concentration, because it's bimolecular, you have the concentration effect, which is killing you in the relative rate. So that's what's generating that competition. Okay? So at high temperature, the barrier can be easily overcome, the rate becomes reasonably high, and hence unimolecular decomposition occurs first, followed by the oxidation then of the smaller radical species that are reduced in that unimolecular decomposition. Whereas at lower temperature, right, you can't there's no barrier, so your fuel undergoes H-atom abstraction by OH, generates the fuel radical, and then the fuel radical reacts with O2 with no barrier to give RO2. And then RO2 generates these carbonyl hydroperoxide species which undergo OO bond cleavage to generate a radical, and an initial, and two radicals, which gives you branching at low temperature. Okay, but I think just look at this slide. I think it's very nice, and it just shows you what happens at low temperature and high temperature. Okay, so at high temperature, then you have to wait until you get to high enough. There's an activation energy barrier to break that CC bond, right? So reactivity doesn't start until relatively high temperature, and then the conversion plateaus out, goes to about 1, where all your fuel is consumed. At low temperature, you have this chemistry where you have no barrier for R plus O2 addition, that you have lower energy barriers for the isomerizations and so on, and then you get conversion at low temperature. So if you only had this chemistry going on, you'd see the conversion would follow the blue line, right? At high temperature, the conversion of the fuel follows the red line. But actually what you see is something in between. You've got this negative temperature coefficient behavior. So what happens there in the intermediate temperature regime is you have this chemistry going on, right? So you have alkyl peroxy radical formation that can give you an olefin plus HO2 directly, or it can isomerize and it can give you a cyclic ether plus OH or beta scission products, okay? And then when you form this radical, these species can form these. Now, there's not much chemistry stemming from this radical here. Most of it goes to a carbonyl hydroperoxide plus OH. I'll talk about that later today or tomorrow, okay? Later today, actually, okay? And then you get these branching products, okay? So at low temperature, if you get branching, right, the reactivity should increase up to here, right? And the chemistry would follow the route through this blue chemistry here, right? But what happens is that the conversion of the fuel turns over and becomes less if you increase temperature. Why? Right? Because what happens is you do form alkyl peroxy radicals, but then there's an activation energy barrier here of about 30 kilocalories per mole to produce an olefin plus HO2. When you go higher in temperature, once you get up to about 750 Kelvin, that 30 kilocalorie activation energy barrier can be easily overcome. And so instead of isomerizing to QOH and going on to branching here, some of these RO2 go to olefin plus HO2. Or they isomerize to hydroperoxy alkyl radicals. I'll explain this later. And then they can go to cyclic ethers and OH, and then some beta-scission products. Again, because these reactions have energy barriers in the 20 to 30 kilocalorie per mole range, which start to then can be easily overcome once you get to about 750 Kelvin, right? And so in these reactions, though, the dot here over the species indicates a radical. So we have a radical producing one radical. These are all propagation reactions, okay? If we went through the low temperature chain branching pathway, we only produce one radical down to here, but then once this carbonyl hydroperoxide decomposes, we get two more radicals, right? So if the chemistry reaches this point here, we've produced three radicals from one fuel radical, right? And we get chain branching. And so if anything competes with that, these propagation reactions are competing with that in this regime, you see the conversion doesn't go to zero, right? It does continue, but it's not nearly as extreme as it was at lower temperature because you're getting propagation reactions competing with the branching reaction, okay? So it doesn't go to zero, but it certainly competes and leads to this negative temperature coefficient regime. What do I want to... Okay, one thing I just wanted to point out here that I just show, and in this diagram here, it's just showing a first addition to O2 and then an isomerization. So you have an alkyl radical addition to O2, you get an isomerization. And then you get a second radical addition to O2, and then you have this hydroperoxide radical, and you get that then produces the carbonyl alkoxy radical plus OH radicals. There has been evidence published by Jiandong Wang, working with Mani Sarathi, that you do get a third and a fourth addition to O2 also, right? But actually, the concentrations of those species that they measure are a tenth of the second addition. So in my opinion, it's better to worry about other uncertainties before we start adding that chemistry into the mechanism. Because if we start adding a third and fourth addition class into the reaction mechanisms get bigger and bigger, okay, and more complicated. And you're only accounting for about a tenth of what, you have 90% of what you need without that, okay? So for me, I'm willing to compromise that loss for the gain that you get in not adding all the species and reactions to the mechanism, okay? So what I wanted to say here, at intermediate temperatures then, what really contributes to this negative temperature coefficient behavior is the fact that the alkyl peroxy radicals can form an olefin plus HO2, and the QOH species that are formed here can give you a cyclic ether plus OH. And those two channels are the ones that are mainly responsible for negative temperature coefficient behavior. Okay. Okay, so I'm going back to the slide now, and we have three distinct regions again. So we have, we have the low temperature range up to maybe 900 or 1,000 Kelvin, where the alkyl radical adds to O2, we get alkyl peroxy, it isomerizes to hydroperoxy alkyl radical, that adds to O2, and we get chain branching, right? At intermediate temperatures then, what happens is the fuel undergoes initially, at initiation, undergoes H atom abstraction, forming HO2 radicals, and we get alkyl radicals. And then those alkyl radicals can undergo H atom abstraction by HO2 to give alkyl radical plus H2O2, right? And then H2O2 can decompose to give two OHs. And then the OHs can abstract a hydrogen atom from the fuel to give alkyl radicals, and then we can get RO2, right? So we get lots of RO2, and then RO2 at intermediate temperatures, and this is the main player at intermediate temperatures. RO2 gives you olefin plus HO2, okay? And then if I go higher in temperature, what happens is the fuel undergoes decomposition to radical. That radical gives you a smaller olefin and will give you either methyl or hydrogen, like I showed you on the board yesterday. And then hydrogen reacts with O2 to give O plus OH, or methyl reacts with O2 to give formaldehyde plus OH. And then formaldehyde undergoes, this isn't branching, it's a propagation. But then formaldehyde is reactive because it'll give you formal, it'll give you H and CO, and then CO will react with OH to give you CO2 plus H. And that gives you a lot of exothermicity, okay, which drives reactivity, okay. But I have these boxes plotted over the area here, and it's one thing I'm going to point out here, and I'd like you to pay particular attention to, right? Because a lot of people, so you can see, look, it isn't until you reach, is this 1250 Kelvin, right? It isn't until you reach 1250 Kelvin that actually you have convergence and all equivalence ratios have the same reactivity, right? So you reach 1250 Kelvin there. But below that, right, fuel-rich mixtures are faster than stoichiometric, which are faster than fuel-rich, or fueline, right? So why is it that these fuel-rich mixtures are faster? We'd say, I understand, it's understandable at low temperature, but why is it that even at 1,000 up to 1,200, 1250 Kelvin, that rich mixtures are still faster? Why doesn't this crossover occur at lower temperature is really my question. Right. So if I go back, right, as I said yesterday, right, the fuel undergoes H atom abstraction, we get an alkyl radical, right? And the higher the fuel concentration, the higher the concentration of alkyl radicals, right? And if you have a higher concentration of alkyl radicals, the higher the concentration, or the higher the chain branching, ultimately. Because from each alkyl radical, you're going to get the branching. So the more alkyl radicals you get, the more branching you get at low temperature. So that explains why rich mixtures are faster at lower temperature. But why are they faster all the way up to 1250 Kelvin? Right? Because you have negative, I said this happens at about 750 Kelvin, right? This turnover typically occurs at 1,000 Kelvin, right? And if we go to the next slide, that's what we see for N, this is for N-pentane, okay? So this is 900. At 1,000 Kelvin, it's already turned over, okay? So at this turnover point, why isn't this convergence happening here? Why does it not happen until it reaches 1250 Kelvin?
Is it because of the olefins? Because then once you're at 1250, you're way past the end of that generation?
I think you're right. So what's your point?
Intermediate temperature olefin generation. Once you're at 1250, you're way past the, like, what was it, up to 1100 Kelvin, I think was the range that was given for that one?
Yes. Well, yes. Okay. It's not fully right, but yes, you're thinking along the right lines. right? So, and I'll show this in a slide a little later. So once you get to 1250 Kelvin at 20 atmospheres, right? And this turnover occurs at slightly different temperature depending on the pressure. And there's a plot I'm going to show you a little bit later that shows you this, right? But once you get to 1250 Kelvin, this R plus O2 gives RO2, no longer goes to RO2, it now stays at R plus O2. And so now your alkyl radicals only decompose to give you a smaller olefin and either methyl or H atom, like the fuel did, right? Or the fuel radicals. Okay, so, well, it is a fuel radical. But really, what's key is this reaction here, right? If you're not getting any RO2, if you don't get any RO2, then you have no RO2 giving you olefin plus HO2. And it's this reaction that's a major source of HO2 radicals in the 1000 to 1250 Kelvin range. And HO2, I should say. Where am I? Where do I have that chemistry? Sorry. The HO2 will abstract from a stable molecule, giving you H2O2, which will give you two OH radicals. And that gives you branching, right, at intermediate temperatures. So the source of HO2 at intermediate temperatures is actually from RO2, right? And RO2 concentration is directly proportional to fuel concentration, right? So therefore, in this, we'll say 1000 to 1250 Kelvin range, again, because the HO2 is coming from RO2, fuel-rich mixtures are still faster than stoichiometric, which are faster than fuel lean. Okay, so that's important to have in your head. Okay, this is a slide taken from Professor Dew's plenary lecture given at the symposium in 2021. I asked him, would he mind sharing the slide with me, and he quite kindly did. So what we see, or what has been recorded, is we see cool flames in the temperature range 500 to 800 Kelvin. You see a warm flame in the temperature range 800 to 1100 Kelvin, and you see a hot flame from 1100 to 2500 Kelvin, right? So what's causing this chemistry? And he's just showing here that the cool flame chemistry, the blue arrows here, is occurring through the low temperature chemistry that I just showed you, right? Then the warm flame chemistry is coming from, where are we? We say we get aldehyde, we get some reactions, but you're getting from the alkyl radical, it's coming from the alkyl radical, reacts with O2 to give HO2 plus olefin, the fuel radical reacts with O2 to give RO2, and then that decomposes to give olefin plus HO2. Then the HO2 abstracts a hydrogen atom from a stable molecule, either the fuel or the olefin, to give you H2O2, and that decomposes to give you two OHs. And so that's what's causing this warm flame. And then at high temperatures, you get, rapid pyrolysis first of the fuel, and then oxidation of the smaller species, and then the hot flame. Okay. This was actually first shown by Professor Maruta and his group at the symposium in 2005. It was backed up by later work. These are all the same group in Japan, right? So they published some work, first in 2005, then 2011, 2012. And it shows they have three distinct temperature regimes for N-heptane oxidation in a microflow reactor. So they have here at low temperature, you see this is a cool flame, light emission. You see blue emission here, and then you see hot emission at higher temperature. Okay, so and this is actually for N-heptane. You've got 80% N-heptane, 20% isooctane, 50-50 mixture, and then you have isooctane down here. Okay, and you only see intermediate and high temperature flame for isooctane. You don't see very much cool flame at all. Okay, so its reactivity at lower temperature is diminished in comparison to N-heptane. Okay, and then this is a slide that Charlie Westbrook kindly shared with me. So if you do a calculation for N-heptane, and you just, this is, I think, is a jet stirred reactor simulation. So if you plot heat release rate, okay, as a function of time and temperature. So you have temperature on the y-axis here, and here's time. And this is just looking at the heat release rate, okay? You get this spike, you get this rather broad, but low intensity emission, and then you get this strong emission again. This is the heat release, okay? And you can see that this heat release is consistent with the low, intermediate, and high temperature kinetics. Okay, so this heat release is predicted by the model, and these peaks would correspond with the light emission peaks that I just showed you here. Okay. Okay, so at intermediate temperatures then, what's important? Okay, so one reaction that's important is the RO2 giving you olefin plus HO2, and the calculation of that rate constant, right? Just to show the importance of this, so here I show a comparison of the reactivities of black is N-pentane, blue is neopentane, and red is isopentane. And you can see actually N-heptane is much more reactive than neo and isopentane at low temperature, right? And actually, neopentane, even though it's highly branched, is more reactive than isopentane in this temperature range from about 750 to 950, almost 1,000 Kelvin, right? Neopentane is faster to ignite than isopentane, right? And then, but once you get beyond about 950 Kelvin or so, neopentane becomes substantially slower, and isopentane actually is similar in reactivity to N-pentane once you get above about 950 Kelvin. So what's happening, or 900, okay. So what's happening there that's causing that? Okay, so if we look at the pentane isomers at 1,000 Kelvin, 10 atmospheres and phi 1, right? And we do a flux analysis. What we see is that in N-pentane, HO2 elimination from RO2 species, about 25% of the fuel flux goes through that reaction, right? Okay, you're getting HO2 from other sources. So HCO, this is coming from high temperature kinetics. HCO reacts with O2 to give CO plus HO2. Methoxy plus O2 gives formaldehyde plus HO2. Ethyl plus O2 gives ethylene plus HO2, a big one. And N-propyl peroxy giving you propene plus HO2. They're all producing HO2. So this is actually, it's a 20% fuel consumed, but it's actually the percentage of HO2 formation, I should have said, okay? So a quarter of the HO2 is coming from the elimination from RO2 for N-pentane. About 20% is coming from isopentane. But actually, it's not possible to get that elimination reaction from neopentane. So let me just show you what that elimination reaction actually is. So if we have N-pentane, we get this radical. Okay, it adds to O2, we get this radical. Okay, so that RO2 can then, it can go through a transition stage where there's a hydrogen atom here, and this a kind of an intermediate, but that will then give you 1, 2, 3, 4, 5 plus HO2. Can everyone see that? Okay. For we can also get okay, and then that can give us, is that right? 1, 2, or okay, it can give you this or this plus HO2. Is that all right? No, but if we look at neopentane, we get the radical. Okay, and it adds to O2. But now this cannot give you a C5 olefin, right? There is no hydrogen on this carbon that can give you the double bond plus HO2. Okay? So you cannot get the C5 olefin in that case, right? So neopentane just cannot do it because of its structure, right? So you're getting less than HO2 formed from neopentane, and because that happens, its reactivity is so much lower in this regime. Because you're getting HO2 from RO2 in the other two cases, the reactivities are actually very similar. Okay. Okay, and then at higher temperatures, what's happening? So you can see the reactivity of isopentane is a little bit slower than N-pentane, but that of neopentane is considerably slower at high temperatures. Okay, so what's happening there? Well, what happens is you get you get the fuel radicals, unimolecular decomposition, you get the fuel radicals, and then you're getting a mixture of methyl and hydrogen atoms. So this is an ethyl radical that's going to give you ethylene plus H. So you're getting a mixture of methyl and H, methyl and H. But in neopentane, all you get is isobutene and methyl. Okay? You get fewer H atoms because the primary fuel radical, neopentyl radical, is going to give you isobutene and methyl, no H. Okay? And hence, it's less reactive at high temperature than the other two. Okay. Okay, so this is just showing you then the relative reactivity of neopentane and N-pentane. Okay, so this is taken from a paper I published in 1999. This is the conversion, CO concentration formed from N-pentane. So if we plot CO concentration, it's a measure of fuel conversion. The higher the CO concentration, the more fuel has been consumed. And what we see here is at 85% N2 dilution in N-pentane, we get quite a lot of conversion. But in 75% nitrogen dilution for neopentane, we still haven't as much conversion as we had in 85% dilution for N-pentane, which indicates that neopentane is considerably slower to react than N-pentane. Okay, and these diamonds is neopentane, the CO produced from neopentane at 85% N2 dilution as well. So if we compare these red stars with the black circles, you can see that the concentration of CO, the conversion of neopentane is N-pentane is 4 times greater than it is for neopentane at 700 Kelvin, according to this figure, right? Okay, so what if we look at the chemistry of what's happening in neopentane, right? And I did a sensitivity analysis, or I did a flux analysis based on the neopentane oxidation at, if I go back, okay, at the turnover point here at about 730 or so Kelvin, okay? And what we see is that, okay, the fuel undergoes H atom abstraction by OH to give neopentyl radical, right? And only about 10% of the neopentyl radical produces isobutene plus methyl, right? 90% of neopentyl radical produces neopentyl peroxy radical, right? And then 85% of the fuel flux goes to the, so this is the RO2. This is the neopentyl peroxy. And then this is the hydroperoxy neopentyl radical. It's 85%. Okay, so of 100 fuel molecules that are oxidized, 85 of them still go to the hydroperoxy neopentyl radical. If I go back, right? I think actually it's here that I did the analysis, down here, okay? So, all right. So what it's saying is that even at this point, right? At this point, right? A lot of the fuel is reacting to RO2 and it's giving you QOH radical, right? But what happens then? So we have 85% of every fuel molecule goes to this hydroperoxy alkyl radical. But then only about less than 40% adds to O2 and goes to branching, right? We have the rest of it, so whatever that is, 35, 45, almost 50% of the fuel is going, a lot of it to the cyclic ether plus OH, and then about 10% giving these beta scission products. Okay, so if you follow the diagram that I showed you earlier, you have the fuel, gives the fuel radical, gives RO2, gives QOH. And then QOH can add to O2 or give you a cyclic ether or other beta scission products. And these are propagations, not branching. Okay? So in this case, even in neopentane, if I go back, we're looking at the fuel flux now. What's happening here, right? At the end of the NTC region. Okay? So the reason I'm going on about this is this, right? When I was started and talking about low temperature reactivity, you'll hear a lot of people say, well, negative temperature coefficient behavior happens because the R plus O2 equilibrium goes backwards to R plus O2, right? And that's not true. So if I go back here, yeah, you just look here, right? So we have the NTC region is happening here, but we still have lots and lots of RO2 being produced here, right? Up to 1250 Kelvin, right? As I showed for N-pentane, right? So it isn't, the low temperature chemistry doesn't change or doesn't go away until the ceiling temperature is reached. And I'm going to show you a plot of that a little bit later, right? The low temperature chemistry doesn't go away until the ceiling temperature is reached. And that ceiling temperature is reached when that R plus O2 gives RO2 equilibrium shifts back to R plus O2, right? What causes negative temperature coefficient behavior is not that, right? It's competition between branching and propagation in the low temperature chemistry. Okay, and I think at that, let's take a break because I've been talking a long time and you're probably wrecked. Okay, so let's come back at 3:25.